So, as I said before, my name is Oles. I'm an applied cryptography engineer, and today we will talk about Boojum. So, yeah, let's start. First of all, uh, let's talk about proving system itself. How are we going, if we want to create some proof system, what we are going to do, like what questions we should answer and figure out how to deal with them. First of all, it's what we are going to prove. Yeah, so maybe I want to prove that I know some primitive hash, or I know like some root of the polynomial or whatever. And the second one is quite more difficult, is how I'm going to prove it. So these two parts are also like a trade-off between them, because if I want to prove more, it's going to be more difficult to prove it. In sense, maybe it will require more difficult technology, or just it would be harder to prove and verify in like computational resources. So yeah, today we will talk about Plonkish arithmetization. So it's a method that explains like methodology, how we can do it, and you need just to choose your arithmetization, and then have some specific format. We will talk about it like on the next slide, and then you can choose some polynomial commitment and prove it. So there are different polynomials commitment. For example, we were using KZG before Boojum. Now we are using Fry. There are also some other commitments like IPA, on which like kind of bulletproofs, and yeah, there are still different research like, papers discussing new techniques. So for now we stick with Fry, and we are not going to talk about polynomial commitments. We are mostly going to talk about arithmetization. More interesting, I would say, more engineering part, because polynomial commitments are mostly about math, and arithmetization is something not so hard to understand and quite interesting. So what is Boojum arithmetization? It's like Plonkish arithmetization, how it works. First of all, we need execution trace, or just a table that shown on the right. So it's something like, like Excel table, which has its height and weights, and we put, like, there are a lot of cells, and we put some numbers there, and then we are going to prove some relations between those numbers. And the relations we are going to prove, you can see on the left side, it's gates, lookup argument, and copy permutation argument. So a couple of things I also want to mention. All elements, all numbers would be field elements. It's because we really want to deal with field, not with some like real numbers or integers or whatever, because field has prime field, so just numbers modulo some prime number have a really good set of properties, and they are also always bounded. So if you multiply different integers, you can get in the result really big integer, but prime field doesn't have such problems. And also there are different trade-offs between height and bytes of this table. So we use something like 240 columns and 2 to the power 20 rows. And how to choose those numbers is kind of questions, but actually you can use any number. The only requirement is that number of rows should be a power of 2, because to make your proofs just efficient, because we want to use FFT in order to accelerate like polynomial interpolation. Okay, just a quick check if yeah, everyone. Yeah, okay, there is no problem that I should add anyone. Okay, just in case. Okay, so let's continue. Yeah, so the height should be a power of 2. Also, you want to keep your weight as small as possible, just because your proof and your proving and verification will grow linearly with number of columns, and it grows like your verification grows only logarithmic in the number of rows because of L15. And if you talk about like okay, it depends on the polynomial commitment scheme, but overall, like more rows is better than more columns. Also, you have some bounds of number of rows and columns, but it's like details. I don't want to keep it too like complex in this part. Let's move on. But if you have some additional questions, you could ask.
Right. So you mentioned that the weight has to be as small as possible. So currently in the slide you have mentioned a width of 240. So, like, is that the standard weight, or like what weight do you usually use in production for writing circuits?
Yeah, why we need yeah, so it's better to make it as small as possible, yeah, but why we need at least like 240? It's because of let me think, because of some gates. We will move to the gates. So some gates are very wide. So one gate is some polynomial equation which is like use only cells on one row, and if you have some really wide gates, so gate, you need like to have a lot of columns. I will also mention it when we will talk about gates.
Okay, sure.
Okay, so first argument is copy permutation argument. What is this argument? It's about, so we have two types of columns. We have variables and witness. Also, quick small reminder, then in zero knowledge we use a lot of word witness, and like in my team, like witness can have like at least, I guess, three meanings, at least two. So when we talk about witness, I want to specify what currently we are talking about witness columns. And when I say witness column, we just say that it's like some columns which we use without copy permutation argument. So what is copy permutation argument? Copy permutation argument allows you just to prove equality of different cells. So for example, in the picture on the right, you can like see two green cells and three red, and copy permutation argument allows you to prove that both green cells have the same value inside and the same about red. So three red cells contain the same number. Also, like it doesn't depend, you can divide your cells into different groups and prove the equality of like the cells in one group have the same value. It's the main idea why we need it. It's to connect different cells. So we use some number, for example, we in the some upper rows, okay, we compute some hash, and then we want to reuse the hash in some further computations. So we need to get it from top and put it to the bottom, and then we need to like prove equality of those cells. And yeah, witness columns and complexity does not depend actually on what sets you have and how many sets. It just depends of number of your columns that you want to make it variable columns. And witness doesn't have like this property, so each cell is unique, and it's related to some other cells only by gates and lookup. In order to prove it, we have like a grand product like this. If you want to know more why it actually has this like shape, it's well described in just the original Plonk article. It's not like too hard. So yeah, you can just search there for more information. But I don't want to explain. It will take quite a lot of time to explain why it actually works. Okay, so let's move on. Then we have gates. What is gate? It's just some polynomial equation that takes some polynomial equals to 0. And what we have here, like this equation should just take some cells on one row as arguments, then like evaluate some polynomial of these cells, and we prove that this polynomial equals to 0. So, for example, the simplest gate, it's we call it Boolean check. So, for example, imagine you have a cell, and you want to prove that this cell is a Boolean, so that it's either 0 or 1. Why we need this check? Because we usually want to use some bits in our VM, or yeah, just we want to prove that some number is actually a bit. And then how we can, but we don't want to say, okay, it's 1 or 0. We just want to check that it's either 1 or 0. So then we can make the following gate, x squared minus x equals 0 on some cell. Then what we have, that this number in this cell, if we raise it to the second power, it would be still equal to itself. Yeah, and it's easy to see that only 0 and 1 satisfies this property. Gate has different parameters. So first of all, it's number of variables, number of witness, and number of constants. You can see it on the right side. So number of variables and number of witness, it's like number of columns we should apply, we should take, so, or number of cells. Yeah, because remember that we apply gate only on one row. So in this case, we have one variable and 0 witnesses. Why? Because it makes no sense, right, to prove Boolean check on some witness, because if we have witness, it will be hard to connect it to some other cells and with some other gates. And honestly speaking, we almost never use witness columns, because yeah, they make proving and verification quite cheaper, because we don't need that copy permutation argument, but actually it makes things much more difficult and harder to deal with. So usually we use variables, variable columns almost everywhere. And what is constant? Also, we have some constant columns. It's just other columns, but they're hard-coded. So the prover and the verifier and everybody knows what are values in these columns. For example, if we compute some hash function, and there are some constant parameters of that hash function, you can just put them into the constant columns to use them, because we use constant columns for numbers that are not going to change from one circuit to another circuit, right? So for one L1 block to other L1 block. And also we have some other characteristics that says a constraint degree and quotient term. So what is constraint degree? Constraint degree is just power of this polynomial. And what is quotient term? It's yeah. So I said that one gate is one polynomial, but actually the truth would be one gate is a set of polynomials. So because sometimes we want to, for example, we have a gate called compute hash. Yeah, Poseidon 2 hash. It's one gate, but actually, what it actually do, it just, it's quite a hard to put such big number of computation into one gate, because then we will have very high degree of that polynomial, and we have our constraint degree is also bounded. So instead, we split it into instead of having one like huge polynomial of degree, I don't know, like 100, we will split it into some set of smaller polynomials, and then it's like we will call those polynomials like quotient terms, and we just group them together into one gate because, yeah, it's just it's like more.
Hey, Oles, before we move forward, I just had a question real quick. My question was, what's the point of having the witness column in the first place? You said that it's much cheaper to just use the permutation copy argument, and I'm guessing it does not affect the proof in any significant way.
Yeah, we want to use witness when it's like, okay, a very good example. Okay, I can give you a very good example on the next slide, I think, which will show like the power of witness. But usually they're always cheaper, but too uncomfortable. Yeah, when it's like cheaper and it's okay to use them, we use them. But usually, like they're cheaper, but then like we need to sacrifice really a lot, and won't write like, yeah, circuits so efficiently. So yeah, let's just move to. Okay, yeah. Here we have like Poseidon 2 gate. So, sorry, what it actually does, it just compute one hash. Actually, it compute round function of a hash. So you have input like 12 variables, you have output 12 variables, because it's like configuration of our hash, and then you have a lot of intermediate values, right? So these intermediate values, you are not going to use them anywhere because you are interested only in the input 12 input variables and like 12 input cells and 12 output cells. So actually, you can use witness columns for all the like intermediate thing. For example, some linear combination, raising to the 7th power, whatever. And the key is, okay, if your circuit is mostly about computing a hash, Poseidon 2 hash, then it will be, you can benefit really a lot for using this witness, yeah, because you can make this intermediate result witness, and okay, you like it's a lot of cheaper. But if you use like let's say Boolean allocator, like some other gates that doesn't have some like intermediate values, much simpler, so you cannot benefit from witness columns.
Right, thanks.
Okay. So yeah, the thing is, we also have like limit on max constraint degree, and yeah, we'll talk about it. And now I want to talk how. So now everything is like quite good. You just take some cells and you can make some polynomial equation if they're on one row. What's next? And how we can efficiently place these gates in our table, yeah, to make it more efficient. So we have general purpose columns. I don't know why there's one over here, don't matter. And specialized columns. So what is the difference? The key point is that actually how our proving system works, you don't just take some, for example, first, second, and fourth cell of the first row, and it doesn't really just apply some gate to those cells. Actually, you apply some gate to all columns. So for example, if we use Boolean check on the first cell, so the first cell, the first row, the first column, right? So the whole first column would be like constrained to be Boolean, because yeah, we don't put it just so we do this constraint for all the column. And yeah, it's how specialized columns works. So for example, you have some red constraint and you want to put it, and then it will like be duplicated for all the rows. But it's not always the case how we want to deal with those constraints. Usually we need like a constraint to use it just a couple of times. So how can we fix it? I don't know. Okay, it's not. But actually what we can do is multiply by some selector column. So it would be, so you can imagine here that we have x squared minus x, then we multiply this gate times some Boolean selector. Let's do like this. Yeah, some Boolean selector, and it equals to 0. Where Boolean selector is some constant column. It's also an example of constant column. So what we have in this case, okay, if Boolean selector if is 0, then the constraint is always satisfied. And if it's equal, for example, to 1, then you actually need to the gate equal to 0. I think it's quite complex, so I'll try to write it. Can I use just some pen or whatever? Okay, let's make a quick note. So you just do like x squared minus x times some bool selector, right? And it equals to 0. So in this case, bool selector would be also a column, but a constant column. So it could be either, usually it's either 0 or 1. So 0 or 1. And you can see that it's if it's 0, then like this gate is like already satisfied. But if it's 1, then we actually will require that x squared minus x equals 0. So using such constant selector, additional column, we could activate or deactivate some gates. And it actually what allow us to do like general purpose columns. So what actually happens here is like on each row, we can activate some specific gate. For example, on the first row, the green gate is activated. On the second row, the blue gate is activated, and then again green, and then again red. Okay, any questions? It's quite a complex part of the presentation.
Yeah, I wanted to ask about like uh, we add more selectors other than only two Boolean selector columns in the general purpose or the specialized ones.
Okay, if I understand you correctly, the question, yeah, so for actually you can like you know, the only boundary here is fantasy. So you can like really think about really complex structures and make a different set of gates and activate it, deactivate them. But here's also a trade-off. The simpler it is, the easier it's going to be to prove. So for now, how it is constructed, you have like a set of gates and you say, okay, I want to make this set of gates I want to put them into general purpose columns. So for example, we have like 100 general purpose columns, and we have multiple gates. Then for each gate, there will be one selector which could activate this particular gate on this row and deactivate all others once.
Yeah, okay, I got it.
Okay, thanks. And the key point that maybe you say, okay, maybe it will be more efficient, for example, to, like put this one, maybe we can fit, like here we have a little bit more space, so maybe we can put some more gates. It could be more efficient. Yeah, it will be more efficient in a sense that we like use our space in more efficiently, yeah, but it will be harder to prove and to verify, because then for one row, for one gate, you need like multiple selectors where you want, yeah. So, and we have, if we use, for example, on this row we use red gate, okay, we can like put maximum red gates, as many as red gates as we can fit in this row. We put them and we activate them all. And the same, for example, here we can fit like 4 red gates into one row, or 2 green one, or 1 blue. Yeah, usually our gate are general purpose, but there are some gates that we make specialized, because when you use general purpose gate, you also need to add like this selector column, and it's quite costly. And also, even if you don't want to activate it almost nowhere, you always like make some computation in case it's like activated. So for example, like Boolean check, it requires only one column, and we have quite a lot of Boolean checks. So we move to specialized row, because we are sure that we could fit like a lot. But in the other case, if for example, you have one gate that is going to be called, like going to be used like a couple of times, maybe 10, maybe 12, it doesn't make sense to make it specialized, because otherwise it will like require, like all the columns that are going to be used in this specialized gate are going to be like just wasted, because you just call it use like couple of upper rows, but you don't need the other ones. Okay, and boundary gate. Yeah, also you can, there's a possibility which we added but almost never use. You can bound gate. So for example, here you can now like make this placement. Why it could be more efficient? Because in this case we have some free space. Yeah, and green columns, you always, as I said before, you, for example, let's say that green gate require you like 4 cells. Okay, so in the left example, you will have like 8 columns for green gate, because there are 2 green gates, and then you need to repeat the gate twice. But in the right example, you need to repeat it only once. You just activate it more with its selector. So actually, as I have said before, actually we don't activate, like we don't put some gate on some cells, we put them on columns. And in the left side, we will like have 8 columns, and on the right side we will have 4 columns. So it makes like green gate twice cheaper, but it's in case we have like quite a lot of space. Okay, any questions? Fine, and just a quick overview what gates you added. You can always like add some custom gates you want, if you want to a little bit rewrite Boojum. You can even find the folder gates and find all gates there. But what gates we use is Boolean allocator, it's Boolean check, x squared minus x equals 0. Also, it's constant allocator when you want to prove that some cell is actually a constant, some specific constant. So it will have like a form like x minus c equals 0, where x would be like variable column and c would be a constant column. That's how you can put some constant into variable column and then prove that it's like placed in a lot of different places. Then we have conditional select. Conditional select is quite cool gate. I'll write it to you. It's like a times b, okay, small a. Oh, okay. Let's x times y plus z times 1 minus y equals, for example, k. Oh, minus k equals 0. But let's write it in this form, like the equivalent, but this one will be easier to understand. Yeah, and also you most likely want to say that y squared minus y is equal to 0. Yeah. So why is called conditional select? Because it actually makes a selection. So here, what first gate says, Boolean allocator, that y is actually either 1 or 0. So it's like a bit. And then the second gate actually says, okay, if y is 1, let k be equal to x. If y is 0, let k be equal to z. So you can see if y is 0, then we have like x times 0, which is 0, plus z is equal to k. So z is equal to k. But if y is 1, then 1 minus y is 0, and this 0, and we have x equal to k. So here we select k would be either equal to x or z, is like depends on y. So it's like conditional select, one of the most popular and interesting gate. So conditional swap is quite similar. Just if y is, for example, y, you swap the variables. Yeah, like you do like this. If it's 0, swap it as it's 1. Conditional 0 checks the same. If some flag is set, we check that it's 0. Also, like parallel selection is just optimization of conditional select when we have like multiple of x and z variants, but we won't use one like y flag for them, and so on. Like these gates on the left are just some basic ones that most likely you will need like a lot, just because you want just because you want to do some, like logical operations. And the gates on the left are more specific for our implementation. So as far as we want to do some like computation, some virtual machine computation, we have some specialized gates for example, 32-bit arithmetic. So we have F, M, A is fill. Okay, M and A is multiplication and addition, and F, I forgot what does mean F, but yeah, it actually something like X times Y plus Z equals the result. So just some gates that make a multiplication of 32-bit numbers. So actually, yeah. And then like the number inside is like you constrain that it's like has 32 bits, and then you perform some like addition, and yeah, some not just usual field addition modulo some prime number, but yeah, 32-bit addition with like carry bit and so on, or multiplication. And this is just because we want to implement some virtual machine computation. And also we have something that like matrix multiplication gate, 7th power gate, and Poseidon 2. So these are gates just for computing the Poseidon 2 hash. And usually we just can use the Poseidon 2 hash. But what is the problem? We have like some fixed weights of our table. Yeah, we don't want to make it too big. Then if like we have like quite a lot of hash computation, we can put Poseidon 2 gate. But it makes computation of hash function more efficient. But on the same time, it requires like a lot of space. It is really, we can really benefit like when we do, for example, some recursion, when we want to prove that we verified some other proofs. Because we have Fry, we need to like compute a lot of Merkle roots, right? Like if you're familiar with Fry, if not, just you can know that in order to verify Fry, we need a lot of hashes. So that's why, okay, then Poseidon 2 gate will be efficient. But what if we like have quite a lot of hash computation, but for example, the most of the circuit is about lookups. Yeah, for example, there is circuit that not Poseidon 2, but for example, there is precompile for Kichak or SHA-256 hash function, a special circuit that computes these hash functions for virtual machine. Then we have like a lot of bit operation. Yeah, mostly the circuits, there's some bit operations, also require a lot of lookups, which allow us to do bit operation more efficiently and so on. But we need to compute hash like not so much. And our columns, if we have like 240 columns, like maybe 200 of them, you know, approximately, I don't remember the exact number, but really a huge number of them would be just busy with lookup argument, not with gates. And then we cannot, like in the remaining columns, we cannot fit Poseidon 2 gate, because Poseidon 2 gate is very wide. It's like 150, it requires 150 cells, so 150 columns. And in this case, also that's the reason why we are going to use like at least 240 or whatever, like why we need quite a lot of columns just to allow Poseidon 2 gate and some lookups. And yeah, so when it's not efficient to use Poseidon 2, we use 7th power gate, which it's just you know, x to the power of 7 minus y equals 0. So y is actually equal to the 7th power of x. And matrix multiplication, if you like, we need to do it, it's just linear part of like Poseidon 2 round function. Yeah. Okay. Any questions about our gates?
Okay, so I was just wondering, so how computationally complex can a gate be?
You can use as many variables as you want. They should just be placed in one row. And the maximum degree of your polynomial, of one polynomial, is like 7 or 8. It like if you use general purpose columns, it's 7, because you also need to add selector, which will increase the degree on one. And if you want to use specialized columns, it's 8. You can use degree 8, right? So yeah, this is the only limitation. And then it could be like as big as you want, but surely if it's bigger, it's harder to prove and it's harder to verify.
Okay, got it.
Okay, so lookup argument. Lookup argument just a tool that so there are different operations like okay, when there are like operations that are easily expressed with polynomials, for example, check the Boolean conditional select that I have shown you, also like just field multiplication, field addition, yeah, a plus b minus c equals 0. It means that c is the sum of a and b. But think about you want to XOR two numbers. Okay, you have one 16-bit number, second 16-bit number, you want to XOR them. You can do it also with gates, but the idea would be like to split each number into bits, then XOR bits, like 16 pair of bits, then again concatenate it to the number. It would be like quite hard. Instead, we can use lookup argument. So what is lookup argument and what is lookup table? So imagine you have like some pre-computed table. Usually we use like three columns, right? So you have table and you can which like there could be like triples of numbers, and you put them all triples that are like, let's say, good. For example, you can make a XOR table. It will be like we use like XOR table of bytes. So the first column is some set of bytes, like the first column is different bytes, the second column is different bytes, and you just take the all pair of bytes, and the third column would be equal to the XOR of the first and the second one. So in this case, you need like 2 to the power 16 of rows, because like first argument have 2 to the power 8 variants, because a byte. The second one have 2 to the power 8 variants. So in total, you have 2 to the power 16 cases of all possible pairs of bytes. And the third column would contain the XOR result of them. Or you can also make AND or whatever. And then when you want to XOR 2 bytes, you don't need actually to do some complex stuff. You need just to prove that this triple of numbers actually exists somewhere in this table. In the same time, you don't actually reveal where it is located. You just prove that it's located somewhere in this specific table. So when we want to XOR 2 bytes, we can just prove, okay, that it's located in the XOR table. These three numbers locate the XOR table. That means that actually XOR of the first and second equal to the third. And yeah, so we have multiple tables that contain, let's say, 3 rows. Actually, you can use like wider tables. Usually we use 3 or 4, but like, okay, we use 3 or 4, but usually we use 3 because some bit operations or some uncomfortable operations, just like okay, we have 2 arguments, 2 inputs, and 1 output. And yeah, that's it. Then yeah, so how can we choose between these tables? We can add 1 more row, so make it 4 or 5 in total, and the last row will tell us the table ID. So we put the first table here, like, and then table ID would be like 0, and then or 1, and the table 2, and here we have 1. So then when you want to prove that like 3 numbers is XOR, you need to put like these 3 numbers in 1 row, for example, with copy permutation argument. Then you want to put some either constant or some other type of cell to like show the table ID, and you like somehow constrain, okay, let it be XOR table ID of XOR table, and then you prove that this 4 numbers is actually located in the big aggregated table. So table ID will just show what small subtable you're going to use. The formula on the right is just if you want to get know more about math behind lookup tables, there is an article CQ. I guess if you have will have some questions after the lecture, you can always write Kogan, because I'm not in the chat, and he will add it to the chat, and I will share like all the links you're interested in, and yeah, whatever. Okay, any questions?
I don't understand how the complexity of calculating those values again is greater than proving that they exist in the table.
It depends on like how much do we save when we use table instead of gate, right?
I'm sorry, can you please repeat?
Yeah, like the question is how much we save when we use table instead of gate, right? Like,
Yes, right.
okay, it actually depends on the table. Some tables, so yeah, but you can try. There is cool article, I guess. Yeah, I think I should find and send you one article if you're interested in arithmetization. It's about different type of arithmetization. It's like, I would say it's completely different than what we're talking about, but it will give you like idea how to deal with some bit operation when you deal with on the gates without lookup tables. For example, let's try to compute if we have like x, we want to do XOR y, right, where x and y are bytes. X or y equals to z. So in order to do it with usual gates, first of all, we need to add some variables like x1, x2, which will stand for the bits of x, x8, and the same for y. Yes, so, and y1 and so on. And for each of this bit, we should make what we should make. We should make a Boolean check. So we also should like add 16 constraints of type x, like xi squared minus xi equals to 0. So we have at least like 16 these constraints for x's and for x bits and y bits. Then we want to XOR them, so we want to make something like that y equal. I don't remember how to XOR, but okay, and make and is simple. You just multiply, and it will be like making and, right? XOR a little bit complex, but I don't know to spend time on remembering how to do XOR, but it's also like not too hard. Yeah, just equations that like do XOR for bit is actually simple, like and whatever. And then you also need like 8 those gates. So 8 those, 16 those. And then in the end, you need to do something like, okay, that equals that like 1 plus 2 times z2 plus 4 times z3 and so on, yeah, to sum all the bits. And you need to do this equation actually 3 times, because you need to do it for z, then for x, and for y. So in total, you get 3 plus 8 plus 16, it's 27 additional gates. And also you got like 16 additional variables. So they also should be like, they also like spend your space in this table, because more variables, more space. And this how it's happened with logical byte tables. But yeah, so other would be like you can compute kind of similar way.
I was just wondering, why are we running the Boolean check on every bit of X and Y?
Why we need Boolean check on every X and Y?
Yeah.
Okay, because in other case, for example, you can, okay, so in order to split, we need to use this equation. Do you agree? Then, like, if, for example, let's assume that z is equal to 2. In this case, we want like z1 equals to 0 and z2 equal to 1. Yeah, like bits, right? And z3 equals to 0 and so on, and all zeros. But and what you can actually do, you can do like this. Let's put like 2 here and 0 here. So the first bit would be like 2. Okay, it's not possible, but it will satisfy this equation. So we actually need also to prove that each of these numbers is 1 or 0.
Okay, thanks.
Mm-hmm. Yeah, and in fact that you don't need to check it for z, because zy is like multiplication of x and y, so it's going to be always like 0 or 1, and so you can say like 8 constraints to not checking that. It's okay. So let's check if I missed something in the chat. Okay, great. Okay, and it's almost over. Okay, let's just quickly continue. And we have, yeah, so the last couple of slides like make it. So yeah, we can have different configurations in our circuit. First of all, we can have no lookup when we don't want to use any lookup. We can have table ID as variable. So what does it mean? Like, so the table ID here, it could either be variable or constant. Why does it matter? Because if you use table ID as a constant column, it's very like simple. Okay, the first, like, you can predict how many rank checks you want, how many like not rank checks, but like source, how many like ors and ends, and what operations you're going to have when you like put table ID in the column as a constant. But maybe you want to make it a variable. Variable would be more flexible, but we also almost never use it because it was like an experiment. Should we like try to optimize something using table ID as variable? But actually, it just requires. It's not so simple to optimize something, and actually, it's even worse. So usually, yeah, we just used table ID as constant. So also you have a whites of the table. As I said, it's like 3 or 4. Usually we use 3. Yeah, I'll show you the list of tables here, what we use. And what we also have is we have share table ID. So imagine you have like a lot of columns for lookup tables. So like 3 columns and other 3 columns and other 3 columns, other 3 columns. Yeah, and for each column, for each 3 column, you also want to add a table ID to recognize to what table you should apply to these like 3 cells. But actually you can say, okay, I want, like a lot of lookup column, but I want only one table ID. In this case, all your lookup columns will share one table ID, and it means that like on one row, only one lookup table would be available. So here lookup ID is very similar how we work with gate selectors in gates, right? So table ID will just activate you some specific lookup table, and you can either go with one table ID for all, like we did in general purpose columns, or you can say, okay, I want like something specific, whatever. And also, you can use specialized columns, or you can use general purpose columns. So you can also add lookup to the general purpose column we discussed here. So it will be like usual gates, and also you will add here lookup gates. But usually we just move lookup to specialized and keep lookup and gates separately. Yeah, and in this case you will have like whites. How many you? Oh, no. Number of repetitions. Sorry, number of repetitions. So how many you want to? Yeah, repetitions. It's quite similar as we have here. Number of repetitions of specialized column when we use gates. Yeah, just number of repetition. And share constants is quite similar to share table ID. Okay, and the now, like, what tables do we have? It's like 8-bit AND table, 8-bit binopt table. Like it will just you put 2 arguments and then you receive AND or like AND or and XOR concatenated. So then you can split and like separate the AND result, the OR result, and the XOR result. Also, it's 4-bit XOR, but XOR of 3 elements. So it's this one, like 4-bit XOR of 3 elements, is an example of a table where we have like 4 elements. So here will be like three inputs and 1 output. We use it for like also for tables for SHA-256. So I most likely need to move like this to the right or whatever. We have byte split table. So what is byte split table? When you have like 16-bit number and you want to split it to 2 bytes, or instead you want like to concatenate 2 bytes to one 16-bit number, then we have like 3 numbers, whatever, like 2 inputs and output, or 1 input and 2 outputs. Like it depends how you want to like name this operation. For example, why it's important, because we cannot XOR 16-bit numbers. Why? Because we have our limitation of table size. Our lookup table should be like not more than our big execution table. It requires some field boundaries, because like multiplicative subgroup of the field, which we use for FFT. But you can just assume that, okay, we have some boundaries, and if we have like want to XOR 2 16-bit numbers, it will require us to go through all the pairs, and it will be like 2 to the power 32, and our limitation is 2 to the power 20, maybe 21, whatever. So on, we cannot. But what we can do, we can add this byte split table. So if we have 2 16-bit numbers, we can use this table to split it to bytes, each number 2 bytes. Then we can use like XOR table to XOR chunks separately, and then we can concatenate again. Yep. And we have a range check. It just checks that usually it just uses the first column and the second 2 columns are just empty. It just proves that also the second 2 columns are just 0. It proves that the first column is like always like has 16 bits. And also here we have like tables for SHA-256. A, B, and C here would be 4-bit elements, and it will like compute, I think, like this. It's just for some SHA-256 internal logic. I'm not aware of SHA-256 actually, and like the algorithm itself, but yeah, it uses such bit operations. And we use this table for optimize SHA-256 computation. Primitive implementing zk, I guess. And then just okay. I guess I have covered what like our minimum, plan, what I wanted to say, but actually here is nothing very interesting. It just tells how we usually implement. So instead of tracking, okay, what cell, okay, here we have already checked that it's Boolean, and then we put it whatever. We just use some abstractions from, it's just, like implementation details. And for example, we have structure Boolean, and we guarantee that the cell inside is always like Boolean checked, or like check that it's a byte, so have 8 bits, has like 256 bits, for example, is represented by 8 numbers of 32 bits, and whatever. And here's some just methods how we do it. And yeah, and we have like different other types that it's just implementation details, like rescue, Kichak, SHA, like modular arithmetic, elliptic curves, and pairing.
I was just wondering whether a negative number can pass the range check, or whether the range check function, or whether it will fail.
Negative number?
Yeah.
So when we deal with prime field, we don't have like actually a negative number. So you mean like, for example, -5, right?
Yeah.
But actually, like, for example, we do something modulo 7, then -5 is just equal to 2, because like it equals to 7, -5 is equals to 0 minus 5, but 0 is actually equals to 7, because, for example, we do something modulo 7, so it equals to 7 minus 5, so it equals to 2. So actually, when we are talking about, okay, we have like a couple of bits, that means that our number is like, if you have some number like and says it's a byte, that it's like from 0 to 255.
Oh, right.
Okay, any other questions? When I have like read it, when I started to do the zero knowledge, I really love it. It's just interesting how, for example, you can make like some conditional selection, or how you can do some trees or other data structures, so you can bit operations or whatever. It's just interesting. I recommend to read it if you got curious about gates, and it's quite simple, so you can maybe finish it just 1 hour. And also I will send you a Plonk article and an article about lookup if you're curious about math behind proving system. But there, of course, will be like, there's a lot of math and more complex.